We think we know time. It marches forward, relentlessly, second by second, minute by minute, an arrow always flying in one direction, from the past through the present into the future. But is this true? Is time really so simple? Consider light, the fastest thing in the universe. Photons, the particles of light, travel at this incredible speed, and for them, something extraordinary happens. Time, as we know it, simply ceases to exist. A photon emitted from a distant star, billions of light years away, experiences its entire journey instantaneously. Albert Einstein. He revolutionized our understanding of space and time. Before Einstein, we thought of time as absolute, a universal clock ticking at the same rate for everyone, everywhere. But Einstein showed us this wasn't true. Time is relative, it stretches and it shrinks. It depends on how fast you are moving. It also depends on gravity. A clock on a spaceship moving near light speed ticks slower. A clock near a black hole also ticks slower. Time was no longer a rigid backdrop. It became a dynamic player in the cosmic drama. Let's talk more about photons. These are the fundamental particles of light, tiny packets of energy. They carry the electromagnetic force. They are how we see the world. They are how the sun warms the earth. One of the most famous experiments in quantum physics is the double-slit experiment. Imagine firing photons one by one at a screen with two narrow slits in it. Instead of two bands, we see an interference pattern. It's as if each photon passes through both slits simultaneously like a wave and interferes with itself. The very act of observing changes the outcome, collapsing its wave-like possibilities into a particle-like reality. Now, let's delve into one of quantum mechanics' most bewildering phenomena. It's called quantum entanglement. Einstein famously called it spooky action at a distance. Imagine you have two quantum particles, say two photons, and they are created in such a way that their properties are linked. They are entangled. This means that even if they are separated by vast distances, they remain connected. If you measure a property of one particle, you instantly know the corresponding property of the other particle, instantly, faster than light. This non-local connection is a fundamental feature of the quantum world, challenging our classical notions of cause and effect being limited by locality. It suggests a deep interconnectedness in the universe. Section 5. Whispers from tomorrow. Does the future influence the past? The strangeness of quantum mechanics doesn't stop with entanglement. There are experiments and theories that explore an even more radical idea, the idea of retrocausality. This suggests that events in the future might be able to influence events in the past, at least at the quantum level. Consider variations of the double-slit experiment like the delayed choice quantum eraser. In these experiments, the decision to observe which path a particle takes can be made after the particle has already passed the slits. It's as if the particle knows what measurement it will encounter in its future and adjusts its past behavior accordingly. This is deeply unsettling to our classical intuition. The effects are subtle and confined to the quantum realm, but they do suggest that our linear, one-way perception of time might be an oversimplification. Section 6. The block universe, all moments, all at once. Given the malleability of time in relativity and its even stranger behavior in quantum mechanics, some physicists entertain a radical idea. It's called the block universe theory. Imagine all of time, every moment from the Big Bang to the distant future, existing simultaneously, like a giant four-dimensional block of space-time. In this picture, the past, the present, and the future are all equally real. There is no special now. Our perception of time flowing of a moving present moment would then be an illusion, a trick of consciousness, perhaps akin to watching a film. All the frames of the movie exist simultaneously on the reel, but we experience them one by one, creating the illusion of motion and narrative. Section 7. Decoherence, the emergence of our perceived time. If the quantum world is so strange, full of superpositions and probabilities, why don't we see this strangeness in our everyday lives? Part of the answer might lie in a process called quantum decoherence. This is how the weirdness of the quantum world transitions into the classical reality we experience. Quantum systems are incredibly delicate. When a quantum system interacts with its environment, it loses its quantum properties. The environment essentially measures the system. This interaction entangles the system with its surroundings. The information about the superposition gets spread out, diluted into the vastness of the environment. It becomes practically impossible to retrieve, so the system appears to collapse into a single, definite state. Decoherence might also play a role in creating our sense of an arrow of time. The interactions that lead to decoherence are generally irreversible. Section 8. Quantum Dreams, Technologies of Tomorrow. The strange and wonderful rules of quantum mechanics are not just for philosophical debate, they are the foundation for a new wave of technologies. Technologies that promise to transform our world, from computing to communication to medicine. Quantum computers are perhaps the most famous example. Unlike classical computers that use bits representing zeros or ones, quantum computers use qubits. Qubits can be 0, 1, or a superposition of both. Thanks to superposition and entanglement, quantum computers can perform many calculations simultaneously. This could allow them to solve problems currently intractable for even the most powerful supercomputers. Then there's quantum cryptography. This uses the principles of quantum mechanics to create unbreakable codes. If anyone tries to eavesdrop on a quantum-secured communication, the very act of observing a quantum state disturbs it. Section 9. The universe staring back our tangled reality. So we return to where we began, our simple everyday understanding of time as a relentless forward-flowing river. It seems so intuitive, yet the quantum world tells a different story, a far stranger, more intricate tale. Light, the universe's speed demon, experiences no time at all. Particles can exist in multiple states at once, only settling into a definite reality when we look. They can be spookily connected across vast distances. The future might even whisper to the past. Our journey through quantum mysteries reveals a universe that is profoundly interconnected, where the observer and the observed are not separate entities but participants in a cosmic dance. The block universe suggests all of time might exist at once, our perception of flow a mere illusion.